In this lecture, we are going to learn how to represent a function as a power series. So represent, so let's say representation of a function as a power series, power series. So in the previous section, we learned about what we mean by a power series. So power series is something like this. So if we can express a series in this form, so we can start with n equals 0 to infinity, some constant and x minus a to the n. So this is what we call power series about a. So this is what we call a power series about or around a. So power series around a. So what we're gonna do, we're gonna talk about how to use this idea to represent the function. So let's start with something that we already know. We're gonna start with the geometric series. So if you start with the geometric series, so that's the kind of starting point. It's a geometric series. So as you remember, what's a geometric series? You start, let's say you start with 1, this is a special case, and then you multiply every time by x. So that means 1, then 1 plus x, and then when you multiply by x again, so you get x squared, multiply by again x cubed, like that. So you know that you can write this as a sigma starting with n equals 0th power to infinity, and then the constant is 1. So it is just to x to the n. And then we also know that if the absolute value of x or the r less than 1, this series is going to converge. So it's going to converge to a over 1 minus r. So in this case, a is 1 over 1 minus x. So that's what's going to happen in this case. So that means this series simply equals to 1 over 1 minus x. For future purpose, we're going to write them in this form. So we can write backward, we're going to say 1 over 1 minus x equal 1 plus x squared plus, like that, which is equal to sigma n going from 0 to infinity x to the n. This is under the condition absolute value of x less than 1. So this is a major result, and we're going to use this a lot. So this is the kind of key point for this whole section. So we're gonna use this a lot. Okay, so this is a key point. Now so where this going to converge? So you can see that this going to converge when absolute value of x less than 1. That means the interval from 1 to negative 1. So in the interval 1 to that's the interval. So that's the so interval 1 to negative 1, this series is going to converge. So if you pick any number between the inside this interval, the series converge in this. Okay, so series converge, the geometric series converge. So now let's try to kind of use this idea to create more. So what you notice is the function 1 over 1 minus x is equals to the series. So that means if we have a function, so let's see the idea. So if we have a function fx equal 1 over 1 minus x, 1 over 1 minus x, so 1 over 1 minus x, that function is equals to this power series. What power series? 1 plus x squared, like that. So this is a power series about a. And one more thing, it converges. Converge means the series gives the value of the function when x is in between negative 1 and 1. Okay, so we can say the series converges to the function value when x is in the interval -1 to 1. So the question, what if it is outside? For example, do you get the value if the x is outside? So we can say, what if x is not in this interval? So for example x equal 2. So you can see that if x equal 2, what's going to happen? If x equal 2, you're going to get 1 over 1 minus 2, which is 1 over -1, that means -1, and you can see that that does not equal to the series. You can see if you plug in 2, what do you get? You get 1 plus 2 plus 2 squared plus, you can see that this side goes to infinity, so that means it's not equal. So that's very important. You can see that. So I'm going to highlight this one here. So you can see that it's not equal if x not in that interval. So you have to be very careful. This power series converge only for certain values. So if you pick anything outside, the function does not equal to that. Okay, so that means you have to be very careful. Function equals to the power series only in that interval where it's going to converge. Okay, so interval of convergence is very important. That's the interval of convergence. Only in that interval the two things are equal. Okay, now let's see one of the application. So I'm going to use this as the starting point and then try to derive like a few more functions. For example, what is the power series of 1 over 1 plus x? Because you know that if the absolute value of x is less than 1, it's going to converge. No problem with that. So and then we're going to use that idea to create more. So let's see. So as a first example, so let's say find the power series of following functions. So let's say find the power series of the following functions. Find the power series of the following function. So let's start with the first one. Let's say 1 over 1 plus x. So let's say your function is 1 over 1 plus x. So if you have something like that, what you're going to do, you're going to match with the previous function. So that's the goal. You're going to match with, you have to bring it to 1 over 1 minus x format, because once you bring it to 1 minus x format, you can plug in that x to the series or the sigma notation. So that's the idea. So let's see how we're going to do this problem. So the question is how to bring it to 1 minus x. What we're going to do, we're going to add and subtract. So what we do, this is equals to 1 over 1 minus x. So that's the trick. So we're going to add an extra negative sign here. Now we know that what you need to do is you simply want to replace x by negative x. That's what you do. So that means you're going to go to that and just replace x by negative x. So it is 1 plus x by negative x is because negative x, and then negative x squared, negative x cube, like that. So that's, we do the same thing in the power series as well, in the sigma notation as well. So sigma n going from 0 to infinity, it is negative. So what do you get? It's a negative x. So it is negative x to the n power. That's what we have. So you simply replace x by negative x. Okay. So what we did, replace x by negative x in star. Okay, that's how we do. So we go to the star and plug in x equal negative x. Okay, so let's simplify the rest. Now what's going to happen? You can see this side is now simply becomes 1 minus x plus x squared minus x cube, like that. So sign changes, and here what's going to happen? You can probably get the negative sign out. So we normally write this one as negative 1 to the n xn. You can isolate xn. So that's the power series representation of 1 over 1 plus x. So what is the interval of convergence? For the interval of convergence, interval of convergence, what we can do, we know this is a geometric series. So since this is geometric series, we know that the r has to be in this case r is negative x, has to be less than 1. So this says that x less than 1, so that means the same thing as negative 1 to 1. So that's the interval of convergence for this one as well. So it's the same answer for both problems, whether 1 plus x or 1 minus x. So you get the same interval of convergence. Interval of convergence means that's only in that interval, the two things are equal. Okay, two things are equal. So let's go for one more. So you can see that it's very clear. And then radius of convergence is still that's a radius. So that's r. So in this case r equal 1. That's the radius of convergence equal 1. Okay, so let's do more. How about this one? So as the next example, let's try to do 1 over 1 plus x squared. 1 plus x squared. So if you have this one, so it is again very clear. We do a similar argument here as well. So what we do, we can write 1 over 1 minus x squared now, because it has to be of that form with a minus sign. This minus sign is important. Okay, so whatever you get extra, put it there. So let's now we're gonna do the same argument. So this is, you can write as sigma n going from 0 to infinity. You're gonna get negative x now. So it is a negative x squared to the nth power, right? Yeah. So then we can expand this. So if you expand this, you're gonna get sigma n going from 0 to infinity, negative 1 to the n, and then you can write x to the 2n. You can write it like that. So if you write few terms, so what are few terms? So so let's write few terms. If you put n equals 0, so you're gonna get n equals 0, you get 1. If you put n equal 1, it is negative x squared. If you put n equal 2, x to the 4th, n equal 3, x to the 6th, like that. So that's the series you get for 1 over 1 plus x squared. So you can get this one from the previous one as well. If you replace x by x squared, you're going to get this one. Okay, what is the interval of convergence? For the interval of convergence, what do you want to do? What we need is negative x squared absolute value, because that's r, has to be 1, less than 1. So this says that x squared less than 1. And this says that if you take the square root inside, well, when x squared is less than 1, that means x less than 1. So you can see that it's the same thing again. So it's the same interval. So that's the interval of convergence. Yeah, what you want to do, you want to simplify all the way up to until you get x. So that's the kind of way to do it. Good. The same thing here. So okay, and the radius of convergence is still 1. So r is also equals to 1. Radius of convergence. Okay, let's do one more. How about this one? The next one, part C. So let's say I'm gonna write the full question here. Okay, let's look at that one. So yeah, so power series representation. So so part C, how about 1 over x plus 2? So the difference is this 2. You can see that in the representation it always has to be 1. So if you look at previous examples, you can see that it's always 1 plus or 1 minus. Even the original one start with 1 minus. So 1 is important. The 1 has to be there. So what you need to do, you need to get the 1 here. So how to get the 1? You can take what we normally do is we can take 2 as a factor out from the numerator, from the denominator. So we can take 2 out as a factor. Whatever the number, you can take it out as a factor. So that means you divide everything inside by 2. That means if you divide inside by 2, you're going to get 1 plus x over 2. So it should be the 1 plus or 1 minus. So that sign is, that's this 1 and this 1 is important. It should be 1 is a plus or minus. Okay, in this case plus. Now we know what to do. So it's very similar to the previous example. So we're going to introduce 2 negative signs. So we can write this one as we can say 1 over 2, and then we can write this one as 1 minus, and then minus x over 2. So that's how we can write it. And after that, then we can just substitute. So that's the one we're going to substitute. We're going to substitute this into the formula. So that means we still have 1/2 outside. So it's going to be 1/2. Go to the sigma notation and plug in whatever we get. So in this case, what we get is negative x over 2. That's what we get to the n power. Okay, it's just the same formula. So this is by star. Okay, by star. And then what we can do, we can simplify this a little bit. So we can write this one as 1/2 sigma n going from 0 to infinity. We can take the negative one out, and then we can write x to the n over 2 to the n. Now what we can do is we can bring this 2 inside, 1/2 inside. So finally you end up getting sigma n going from 0 to infinity, negative 1 to the n, x to the n, 2 to the n, that's 1 more, so 1 plus 1. So that's the final answer for this one. So you can write this series in this form. So this is the power series representation of 1 over x plus 2. X minus 2 also do the same way, but you don't need a negative sign in this case. Okay. So again, what is this so we can say the series converges when the r means negative x over 2. So when the r, so this is r, the absolute value of r is less than 1. That's the r. Okay, it's a power series, so I can write this one here. So in this case, it's a geometric series. So r is x over 2. That's the r. Because we normally write a to the rn, or rn minus 1, or a rn minus 1. So that's the r. R is negative x over 2. Okay, and then as before, we can simplify this one. So how to simplify this? The negative sign you can ignore. So what you're going to get is you can multiply by 2. So you're getting x less than 2. Okay, so that's the r. So r equal. Now this is a big r. That's a small r. The ratio. This is the ratio. This is a ratio, but this is the radius of convergence. The radius of convergence. Good. So this is what is the r? So in this case, so that means x is in between negative 2 to 2. So that is the interval you are talking about. So it's only converge in this interval, negative 2 to 2. If you try to plug in anything else, they are not equal. The power series and the function have 2 different values. Okay, as the last example of this type, let's do this one. How about this x3 over x plus 2? x3 over x plus 2. So this is very similar to the previous problem, but the only thing is we have x cube here. So if you have x cube, what we normally do is we're gonna do the way we did before. We're gonna just isolate x3 and then write x plus 2, and x plus 2 you handle as we did before, because from the previous example we know that the 1 over x plus 2 is equals to what? It was sigma n going from 0 to infinity, negative 1 n x to the n 2 to the n plus 1. That's what you get from the previous example. So so this is coming from here. Now what we're gonna do, we try to bring x3 inside. That's very easy to do. So if you try to bring x3 inside, what's gonna happen? Just increase the index of x by 3. That means sigma n going from 0 to infinity -1. What you want to do, you multiply by extra x 3 times x, so that means it's become x to the n plus 3. There's nothing in the bottom, so it's 2 over 2 to the n plus 1. So if you write a few terms, so you can plug in n equals 0. If you plug n equals 0, what do you get? You get positive sign, you get n equals 0, so you get 1/2 x to the third. So it's become 1/2 x to the third, and then minus, because n equal 1 minus. Now plug n equal 1, so that means x fourth, 1/4. So it's a 1/4 x to the fourth, and then n equal 2, that means positive, so it's a 1/8 x to the fifth, like that. So those are the extra few terms, and you can see the radius of convergence is still the same. So what you can do is you can just take one of these terms. So you can see that even though you multiply by x3, the r is still the same. R is still -1. So you can see r is the terms which has a n in there. R is a term which has an n in there, so that means it is negative, and then x and a 2. So those are the only ones which has r in there. I'm sorry, these are the only terms which have a n in there. Okay, so so terms with n. So these are the terms with n. Okay, so you have a -1 has the n, x has a n, 2 has a n. So those are the, and then as before you can see, so it is very similar to the previous problem. So take the absolute value of that, and then you can see that. So and then what you want to do is, this has to be, because this geometric series is coming from a geometric series, so this has to be less than 1, and then it's gonna say that x less than 2. So it's the same thing, -2 to 2. So that means even if you multiply by x3, it did not change the interval of convergence or the radius of convergence. Okay, so let's do one last example. So this is the last one of this type, so this might be helpful for the homework. So what if you have a this kind of expression on top? So this is e, I forgot, I think this is yeah, this should be e. So so this one is let's say you have function fx equal, let's say you have x minus 1 over x plus 2. So it is very similar to the previous one, but you have x minus 2 now. So there are two ways to do this problem. So one is you can split this into two fractions and then find the series of the first one, find the series of the second one. So one way to do this is x over x plus 2. You know how to do this one now. Look at the power series and multiply by x minus 1 over x plus 2. So write the 2. So you can write 2 power series. I will not do the whole problem. So write the 2 power series and then combine them. Or I'm going to do this in a different way. I'll say, oh, let's do this way. What I'm going to do, I'm going to write this function in a different way. What I'm trying to do, I'm going to create x plus 2 on the top. So that means if we write x plus 2 here, if you subtract, we will get a minus 1. So that means subtract 3. So that's the trick. If you do that, then this one, if you divide the first one, you get 1 minus 3 over x plus 2. Now what you're going to do, we're going to substitute for the second one. So that is the trick. You substitute for this. Okay, substitute for that. Because we already know what is this. So if you substitute, what's going to happen now? It is simply 1 minus. So what you can do is, if you want to do the whole problem, you need to get the 1 in the bottom. So to get the 1 in the bottom, there's another way to do that. You can divide the top and bottom by 1. So if you do that, it is 3 over 2 and this become 1 plus x over 2. So what you did, you divide the top and bottom by 2. Now the same trick as before. So this one you can write as 1 minus 3 half, because you have to put a negative sign here, 1 minus x over 2. So it's just the same problem as before. So it's 1 minus 3 half. I can have 3 halves outside, so this simply becomes sigma n going from 0 to infinity negative x over 2 to the nth power, like by star, the very first formula. And then we can expand as before. So if you expand this, so what you're gonna get is sigma 1 minus 3 halves sigma. So this is just very similar to the previous problem. I'm just writing everything because this is what you need to do in a general problem. So xn over 2 to the n. Now I can bring certain terms inside. So what I can do is I can bring 3.5 inside. So if you bring them inside, so this is gonna be 1 minus sigma n going from 0 to infinity negative 1 to the n 3 times x to the what, t times x to the n, no changes, but in the bottom it is 2 to the n plus 1, because that's extra 2. So that's what you get. So that's the power series representation of that. And what else you can do is actually you can write out the first term. So if you write out the first term, what are you gonna get? If you write the first term, you're gonna get 1 minus. If you plug in n equals 0, so you're gonna get, what do you get if you put n equals 0? You're gonna get 1 minus 3 halves, and then that's n equals 0. If you plug n equals 0, just plug n equals 0. If you plug n equals 0, you're gonna get positive 3 over 2. Okay, that's that term. And then now let's, and then with this negative sign in front, it's become negative. Now what we're gonna do, I can actually write, the pull extra negative sign out from this one. So if you pull extra negative sign out, so what's gonna happen? Minus. Now let's start with the next term. What's the next term? Because you already start with the 0, start with n equal 1 now, because you already plug in n equal 0. So that means you're gonna get n equal 1 now, because you evaluate the first term. So that means that's gone. So you only have negative 1 to the n 3xn. No changes here. There are no changes. Only you change the index here, because you already evaluate 1. So now you can simplify the first two terms. So if you simplify the first two terms, you're gonna get negative 1 half. That's the first two terms, and then minus sign n going from 1 to infinity negative 1 to the n, and then we have a 3 here, so it's a 3xn divided by 2 to the n plus 1. And then also there are a lot of other things. If you don't like this negative sign in front of the sigma, you can write this on as negative 1 half plus, just introduce one more negative sign here, so it's become negative 1 n plus 1, write it like that. So that means you have one more extra negative sign. That's gonna take care of the sign change, and this is 2 to the n plus 1. So that's the power series representation. And as before, you can see that the converges on, look at the ratio is still the same. Even if you multiply by a number, it doesn't change the ratio. So ratio is the one that you have n. So that means as before, it is still this, so less than 1. That's gonna give you the same interval, negative 2 to 2. Okay, the same r. Okay, so that's how we do. But I did like several extra steps here just to tell you what we can do in a problem like that. But this is what we do. So if you get a term like that, try to do this trick. So this is the trick. So I highlight that. So that's the trick. Try to get the x plus 2, the same denominator as the bottom term. Then you can write this as 1 minus something, and then just do only one. Or as we did before, you can write 2 sigmas and then combine them into one. Okay, so those are kind of things that we can do. So let's go to the next major result. So what's the next result is, if we have a power series, you can do like kind of really amazing things with that. You can differentiate them. You can differentiate and integrate. So what you can do is, so we can say, so we can differentiate, or integrate term by term. It's called term by term. So that's the kind of idea. So we can differentiate or integrate term by term. Okay, so let's try the theorem. So what the theorem says, if the power series sigma c n x minus a to the n, that's the general one, has the radius of convergence r, has the radius of convergence r, has the radius of convergence r. So let's write uppercase r here, just to avoid the confusion with the ratio. Radius of convergence r, which is we can say as positive. So we can say then the function defined by fx equals sigma c n x minus a n. We know that we can write it like that, so it goes from 0 to infinity, is differentiable. Okay, differentiable and also integrable. Integrable is clear, but it says that it's differentiable. So differentiable, and we can write these two results. So what's the first result? If you take the derivative, you can just take the derivative of both sides. So we have the sigma notation, sigma n going from 0 to infinity, c n x minus a n. This is simply equals to, what we can do, we can switch, we can take the sigma out, we can put the derivative in of c n x minus a. So this is very interesting. That means you can do term by term differentiation. You can switch the sigma and the derivative, and also you can switch the integral. So that means you can integrate this sigma n going from 0 to infinity, c n x minus a n dx equal sigma. So we switch the sigma and the summation. That's how we did. We switch the sigma and the summation. So you can integrate first. So cn x minus a n dx. You can see this, we just need the power rule. So that's the major result, and it says that you can differentiate a power series and you can integrate a power series. So it's a very powerful result, and we can use this a lot. So if you have a power series, you can just take the derivative, and then the most important part, the radius of convergence. The radius of convergence does not change. The radius of convergence the radius of convergence of these new functions, of these functions, are still r. So that's the important part. It's still r. It doesn't change. The radius of convergence does not change. Okay, radius of convergence does not change. So let's look at some examples. So what it says that you can differentiate and you can integrate to get new functions. So I'm going to put this in a box because this is the most important part that we need. Good. So let's see how we can apply this in a problem. So let's say, so the example, express 1 over 1 minus x squared as a power series. And find the radius of convergence So if you get a problem like that, what do you want to do? You want to think of what function this is the derivative. Okay, that's the kind of question that we're trying to do. Of what function? So we can see what function has 1 over 1 minus x squared as the derivative. We ignore signs and constants. We ignore signs and constants. Or extra powers of x. You can manipulate all of them. You can manipulate signs, you can manipulate constants, you can also manipulate extra powers, because when we do x3 over 1 minus 1 plus x, so you can always multiply by x, so that's not a problem. So we only need to worry about the major term. So you see that, so those are the kind of things that we need to focus on. What function has this as the derivative, and then forget about the rest. Forget about the constants and numbers, and then extra powers of x. So we know that when you have a quotient, when you take the derivative, it increases the power. So that means we notice that notice this one. So we see that 1 over 1 minus x squared is we can say closely related to the derivative of 1 over 1 minus x. So that's the starting point. Once you take the derivative of 1 over 1 minus x due to the quotient rule or by the chain rule, and we know that you're going to get 1 over 1 minus x squared. So that's the whole point. So that's the starting point now. So so let's say note that 1 over 1 minus x, which is 1 plus x squared, like that, equals sigma n going from 0 to infinity x to the n on x less than 1. Now we take the derivative both sides. So take the derivative of both sides. Okay, so once you take the derivative of both sides, what's going to happen on this side? So due to the chain rule, because this is 1 over 1 minus x, so it's a differentiate 1 over 1 minus x. This one you can write as derivative of 1 minus x to the negative 1, so which is equals to negative 1 minus x, that's the power n, and then negative 2 times negative 1, that's what you get. So that's on this side. On the other side, what do you get? On the other side, what you get is just do the term by term derivative. So you're going to get, so we're going to take the derivative of this. Okay, take the derivative of that. So if you take the derivative of this, what do you get? From the first term you get 0. From the second one you get a 1. Third one you're going to get 2x. Then you get 3x squared, like that. Or you can do the same thing with the power series representation. So in the power series representation, what's going to happen? You can see that the first term is 0. Whether here the first term is when you plug in n equals 0, you get 1. The derivative of that is 0. So that means that term going to go away. So so you're going to get, so we can write this one as sigma n going from 0 to infinity. If you take the derivative, it becomes n x n minus 1. That's the derivative of that. Okay, but when you plug n equals 0, this is gone. So that means you're going to only start with n equal 1. So every time you take a derivative of in the power series, the first term going to go to 0. So that means you start with n equal 1. Nothing change inside. So the only change here is you start with n equal 1 now, because the first term is 0. Okay, when you plug n equals 0, you get 0. So now, so that means that's the answer. So that means your answer is simply so this gonna give 1 over 1 minus x whole thing square equal sigma n going from 1 to infinity n x to the n minus 1. Okay, and the radius of convergence is still the same, because we know that when you take the derivative, radius of convergence does not change. So r is still 1, because it does not change. Okay, so that's the answer. So 1 over 1 minus x squared is equals to 1 over 1 minus x squared is equals to sigma n going from 1 to infinity n x n minus 1. Okay. Now I'm going to tell you one more thing. Actually, let's erase this one. I have to write something here, something extra here, something different here. So there's one more thing. So you can make an index change if you want. So we can write the exact same thing, because when you plug in n equal 1, you're going to get 1 x n minus 1. If you want to start with n equals 0, we can do that. So let's say you want to start with n equals 0. So if you start with n equals 0, that means you're going to start with a lower number. So that means you have to add extra 1 here. That means n become n plus 1 and x become not x n minus 1, it's be x n. So that's the final answer. So you can write it like that. It's n plus 1, not n plus x. n plus 1. So you add an extra 1 there. You increase by extra 1 just to match. So that means if the index goes down, increase by 1. So it's like a balance. It's like a balance. So if this side goes down, this side goes up, like a balance. So if it down by 1, so up by 1. So that's what you do. So if this goes down by 1, that means n equal 1 goes to n equal 0. So down by 1, so up by 1. Okay, and then also we know that the r does not change. So r is still the same. So r is still 1. No change. Okay, so this is the kind of trick that we can do. So if what you need to do is you need to think about what function has that as the derivative, and from that we can just think of that, and then always start with the geometric series, and then try to think of taking derivatives, and once you take the derivative, you might get the function that you want. Okay, good. So let's do one more like that. Yeah, so let's do a few more examples, because this is one of the important one. So the next one is this one. Find the power series representation of find the power series representation, power series expansion of ln 1 plus x, ln 1 plus x. Okay, so what do you want to know? You want to think whether there is a function that has ln 1 plus x as the derivative, but that's not easy. But we know that we have a function that has ln 1 plus x as the integral, so we can start with that one. So so let's say note that the integral of 1 plus x dx equal ln 1 plus x plus c. So we know that. So that's the starting point. That means we can start with 1 over 1 plus x. Okay, so we can start with 1 over 1 plus x, and then this is as before 1 minus we did this before, so you can use that, and this simply become 1 minus x plus x squared minus x3, like that. So if you want to write this one as so this is, so what's going to happen, this is sigma n going from 0 to infinity negative 1 to the n xn, and along with x less than 1, that's the radius of convergence. Now once you integrate both sides, so integrate both sides. If you integrate both sides, you're going to get ln 1 plus x on this side. You can write the absolute, I just ignore the absolute for the moment, because we know that under the radius of convergence, this is always positive. So then the integral of 1 plus x dx. Now what we do, we're gonna integrate term by term. So sigma n going from 0 to infinity negative 1 to the n xn dx. We switch the sigma with the integral, and also we can actually pull the negative 1 to the n as well. We don't need that, so we're going to pull that as well. The integral of xn dx. So this is going to give sigma n going from 0 to infinity negative 1 to the n. So you're going to get x n plus 1 over n plus 1 plus c. Okay. So, and then let's try to write the terms. So you can see that if you start writing n equal, now the question is we don't know what is the c here. So so what you can do first is you can do the index change if you want. So let's make an index change. So I'm going to start with n equal 1. So we start with n equal 1. So if this goes up by 1, inside has to go down by 1. So it is n minus 1 x to the n plus c. So still the same interval of convergence, no change. So what you do, you up by 1. So this one is up by 1. So this is down by 1. So up by 1. This is down by 1. Okay. It's a balance. So you increase by 1 because see it's still the same terms. Okay. And if you want to expand this, so what do you get? If you just try to expand. So what's the first term? When you plug n equal 1, you get x. When you plug in n equal 2, you get x squared over 2, and then x3 over 3, x4 over 4, plus like that. Okay, so that's what you get. Either way, so you can get that. So that's the power series representation. I mean, you can even leave the sigma on, but still there's a c in there, so that's not good. So what we need to do is we need to find the c, So let's try to find the c. So actually plus c, plus c. So for that, what we're gonna substitute? We're gonna substitute something that we know. So let x equal 0. You need to plug in something in the interval. So if you plug in x equals 0, you're gonna get ln 1 equal, you can see all those terms are 0 like that, and plus c. This says that ln 1 equals 0, so this says that c equals 0. So c is 0. So c is 0 means then you're gonna get the final answer like this. So your final answer is ln. You always need to find the c, plug in by something. So so as a sigma notation, it is n going from 1 to infinity, negative 1 to the n minus 1 x n over n, or if you expand it, you're gonna get x minus x squared over 2 plus x3 over 3 minus like that. This is valid for x less than 1. So that's the power series representation of ln 1 plus x. It's very easy to find. What we did was we just integrate. Okay, so we just integrate the 1 plus x function. Once you integrate the 1 plus x function, you end up getting this. Okay, so let's do maybe 2 more examples before we finish this section. So how about ln 1 minus x? Because you can plug in anything inside the interval. So what we can do, put x equal negative x. If you plug in x equal negative x, what's going to happen? It become ln 1 minus x. You simply replace x by negative x. So what's going to happen here? Sigma n going from 1 to infinity, negative 1 to the n minus 1. This is negative 1 n over n. So you can see that you get another negative sign. So this is sigma. Let's see how it simplifies. Negative 1, you're going to get 2n minus 1. Negative, and then this is just x now. This is just x because you took the negative sign out. So it's xn over n. That's what you get. But negative 1, 2 to the n, this is odd. You see that this number is odd number. It's odd. See, this is odd number. This is always negative. It's always negative. So this is always equal to negative 1. So you can pull it out. So if you pull that out, you're going to get negative sigma n going from 1 to infinity xn over n. That's what you get. So that means all the terms are negative now. So it is just the negative of the previous one. It's a negative and nothing else changed. Negative x. So you can pull the negative sign out. So everything positive inside. You can see all the terms are negative, but still this is valid under x equal. So that's how you do. That is 1 minus x. So you can see all the terms are negative, but still only valid for x less than 1. Okay, let's do something interesting. How about this one? Find the power series for how about the function fx equal tan inverse x. Tan inverse x. So again, you want to think of whether there's a function which has tan x as the derivative or which has tan x as the integral. But we know that there's a function which has tan x as the integral. So we start with not that the integral of 1 over 1 plus x squared dx is simply equals to tan inverse x plus c. So that's where we're going to start with. Okay, that means we're going to start with 1 over 1 plus x squared and take the integral. So So let's do that. So tan inverse x is equals to the integral of 1 over 1 plus x squared. We already did 1 over 1 plus x squared. I'm going to use that. So it was 1 minus x squared 1 plus, because you just need to replace in the original geometric series x by negative x squared. That's what you want to do. So like that, and then dx. So if you integrate this one, you end up getting a x minus x3 over 3 plus x to the 5th over 5th minus x to the 7th over 7 plus like that plus c. As before, just plug in something that you know. So let x equals 0, then tan inverse 0 equals 0. So this implies c equals 0. So that means finally we're going to get tan inverse x is simply equals to x minus x3 over 3 plus x5 over 5 minus like that. How to write this as a power series? You can see there are only odd powers. So that means we can use 2n plus 1 here. So n from 0 to infinity, and there's a sign change, so there's a negative something and then this is x odd power, so it is a 2n plus 1 over 2n plus 1, but there's a sign change, so just see whether we can fix that. So when you plug in n equals 0, you should get a positive 1. That means this has to start with n. So that is the power series representation of that. And the radius of convergence is still 1, so r is still 1. You can get that from the ratio test. You know, the radius of convergence is coming from the ratio test, or this is a geometric series, so we get that from geometric series as well. Okay, good. So let's do one last problem. So this is the last problem of this type. Let's do a little bit more here. So this is the problem. This is the last problem. So evaluate the integral 1 over 1 plus x to the 7 dx as a power series. Evaluate as a power series, and then let's do this one. Approximate approximate 0 to 0.5, the same one, dx. We can say correct to within 10 to the negative 7. That's really strong. 10 to the negative 7 is a very small number. Okay, there are 6 decimal zeros. So we can do this kind of interesting problem using this one. So let's do the first part. So the first part is we know what to do with the first part. So we can write this as a power series first, x to the x7. That means you're going to replace x by negative x to the x7 in the original series. So that means we can write this one as 1 minus x7. So if you do that, this is sigma n going from 0 to infinity, negative 1 to the n, x to the 7. X to the 7n, x to the 7n. So if you write a few terms, it is 1 minus x to the 7 plus x to the 14 minus x to the 21, like that. And this is going to converge only in this because it's a geometric series. Now what we do, integrate both sides. Integrating, you're going to get 1 over 1 plus x to the 7 dx is the integral of sigma n going from 0 to infinity, negative 1 n x to the 7 n dx. We're going to switch the integral with the summation. So, and then also pull the negative sign, so it is x to the 7 n dx. So this one, sigma n going from 0 to infinity, negative 1 n x to the 7 n plus 1 over 7 n plus 1 plus c. So if you write first few terms, so it is x minus x to the 8 over 8 plus x to the 15 over 15 minus x to the 22 over 22, like that, plus a c. And this again converge when the ratio, that means x to the so like converges when the ratio, this is negative x to the 7 less than 1. This implies that x less than 1 as before. Now so you're gonna see that there's a so now for the second part, so what we want to do it, we want to evaluate this one. So to evaluate, so what we can do, 0 to 0.5. So 0.5 is 1/2, so it is 1 over x 1 plus x to the 7 dx. So you know that we can pick any c, so we can pick c equals 0 in the definite integral. So that means if we evaluate this one, x minus x to the 8 over 8 plus x to the 15 over 15, like that, we put 1/2 or 0.5, that's okay. So we put 1/2 0. So what are you going to, when you put 0 is gone, but when you put 1/2 you get 1/2. So you're going to get 1/2 minus 1 over 8 2 to the 8 plus 1 over 15 2 to the 15, like that. So that is the sum. Good. So how to answer the last part? So say approximate correct to within 10 to the negative 7. You know that this is an alternating series, and then we know that the error is in alternating series. Okay, so this is a alternating series. So this is a alternating series, and then we know that the error is, when you approximate error is less than the first missing term. So when you have alternating series, we can write it like this. So it's an alternating series because there's a negative sign here. When you write alternating series like this, negative 1 something here, n minus, it doesn't matter, bn, that's alternating series. It says that if you cut at n point, if you cut at the Sn part, the error, there's an error is less than or equals to the first missing term, that means a bn plus 1. So what do you want to do? You kind of do a trial and error approach. So use a trial and error approach. So if you use a trial and error, what you do, you're going to calculate, evaluate few errors. So for example, so let n equal 4. Let's say you're going to go up to 4 terms. So if you go up to 4 terms, so what's going to happen? Then the error, so that means you're going to go to the next term. So the error is what? When you say n equal 4, the error, so you're going to go to the actual series and plug in the next value. So if you want to go up to n equal 4, just plug in, so go to the general term and plug in the next value. So what's the next value? So it is 22. So let's try a few more terms. So what are the few more terms? So we have 1 over, the next term is 22, 2 to the 22, 2 to the 22, and like that. So if you go over the first term, what's the fifth term? So let's say you want to approximate by the first 4. So this is a trial and error guessing. So let's say, so that means for the next term is 1 over, so the error, that means the next missing term is 29, 2 to the 29. So you might need to use a calculator. If you use a calculator, you're going to get 6.4 10 to the negative 11. Okay. But the problem says has to be 10 to the negative 7. And then you can see that if you calculate the previous value, there's a large error. But so this is the next one is going to satisfy. That means this is the error. So that means error is within the correct range. So error is within the range. Error is within the range. So that means you only need the first 4 terms. So that means so correct to within 10 to the negative 7 is asking is just get the first 4 terms. That is 1 to the 1 plus x7 dx equal approximately equal 1/2 minus 1 over 8 2 to the 8 plus 1 over 15 2 to the 15 minus 1 over 22 2 to the 22. So if you use a calculator, you're going to get approximately 49951713774. Okay, so don't write more because it should be only correct within 10 to the negative 7. So only have 7. So you write just the next one. Okay, good. So that's the answer. So you can see that how accurate this technique is. So you can get an answer which is correct to within 10 to the negative 7. So this is a trial and error guess. So what you do, you're gonna calculate few terms, start from the beginning, and then until you reach 10 to the negative 7. So sometimes you will get it, sometimes it will pass by that number. In this case, if you get 3 terms, the error is bigger than 10 to the 7. So for n equal 3, error is bigger than 10 to the negative 7. So that's why we go for n equal 4. Okay, so that is the reason to pick n equal 4. So if n equal 4 doesn't work, go to n equal 5. So like that. So good. So that is the end of power series representation of a function.